Hi everyone and welcome back. In this video, I'm going to go through interfaces in Java. I'm going to first talk about the comparable interface, which is an interface that's provided to us by Java. Then I'm going to talk about how we can define our own interfaces in order to achieve something called polymorphism. All right, so I've already got a project in IntelliJ open here. It's called Interface Fun, and it's got two classes. Let's start with circles in circle.java. So this is a pretty standard circle class. In fact, I've derived this class in previous videos, so feel free to check those out if you'd like to see how I came up with this. Circle has two fields. It has a center of type point and a radius of type double. The definition for the point class is nested as a static nested class inside of circle, and it's just down here, a point has an x and a y. Everything else here is pretty standard. You've got your getters and setters, your toStrings, and that's pretty much it. Some default value constructors and explicit value constructors. All right, moving back to main, which is in a class called interface tester. I've got some print lines here that test out compare to and equals for strings and objects. So I'm going to use this to motivate why the comparable interface is provided to us by Java and why we would use it. All right, so I would encourage you, if you're following along, to type up this code and run it, or take a look at my output right here and see if you can answer these 6 questions here. Go ahead and pause the video and try it out. All right, so let's go through each of these questions. The first one, what does compare to return when invoked with a string? Well, if we look at output 1, we've got zags compared to apples. And if you recall your ASCII values, I'll just make a little note here. The ASCII value for A is 97, and the ASCII value for capital A is 65. If you only remember these two ASCII values, you should be good to go because you can always derive, any other letter in the alphabet by adding its offset to 97 or to 65. As far as special characters are concerned, probably learn those on a need-to-know basis, but these two are really good to know. All right, so we know that there are 26 letters in the alphabet, which means that from A, Z is 25 letters away, which puts Z at 122, okay? 122 minus 97 is 25, okay? And you could go through and test out some of these other numbers and see that what compare to is doing is going character by character, and if there's a difference, then returning the difference in those characters' ASCII codes. So I'm not going to write that all out because it's a little more detail than we need. But what I am going to write out is kind of a general summary of whether the sign is positive, negative, or 0. Because we're not too concerned with the actual number, just its sign, because its sign is what tells us the most valuable information, which is how do two strings compare to each other relationally. Okay, so when the value that compare to returns is less than 0, then that means that the invoking object, or the invoking string, is less than the argument object. So what do I mean by invoking object? So in output 1, the string zags is the invoking object, and the string apple is the argument object. And you know that compare to is non-static because you need an object in order to invoke it. All right, so the opposite is true for greater than 0. And when compare to returns 0, then the invoking object is the same as the argument object. Or in this case, like right here, output number 4, zags compared to zags returns 0 because zags and zags all lowercase is the same string. All right, when would you use compare to? So you use compare to whenever you need some sort of relationship based on ordering for strings, right? And when would you be interested in ordering strings? Well, the most general obvious answer here is sorting. But really output anytime you need some sort of ordering. But if I wanted to sort, say, an array of strings, then I would want to be able to compare strings to find out in which order two strings should be. All right, next, what does equals return when comparing strings? Okay, so we've got two examples of that here. So output 5 is true, zags equals zags, all lowercase, but output 6 is false, zags lowercase does not equal zags uppercase. All right, so what this returns is a Boolean, and it's true when both references refer to the same string, false otherwise. And what I want to emphasize here is when I say the same string, what do I mean? Well, what I mean is the same object in memory, because we know that strings are immutable in Java. I'll write that out because it's kind of hard to hear. Strings are immutable, which means they can't be changed. So every time we declare a string object like zags and zags, which are the same, two different string objects aren't being created. Only one string object's being created, and then two references to the same string object are aliased. Okay, this is a compiler optimization technique, right? What's the point in declaring two different strings in memory if they're the exact same and they're constant, they're never going to change, right? No need to keep track of them separately. If you've already created the string, just give another reference to it. All right, so when comparing strings, I mean both. They're the same string character by character, and they're also the same object in memory. Now we're going to move into talking about equals when we're comparing circles. So I've created a new circle here using a default value constructor, and in output 7, I'm asking, okay, does my circle equal my circle? And the answer is true. My circle refers to the same object in memory as my circle. However, on the next line, I'm creating two different circle objects, both using the default value constructor, so they have the same values, and this returns false. Okay? So this is an object in memory-based comparison, not a value of the fields-based comparison. So what does equals return when comparing circles? Also a Boolean. So this is true if both references refer to the same circle, false otherwise. And then in general, what is the purpose of equals? The purpose of equals is to compare if two references refer to the same object. Okay, and it kind of seems like I'm repeating myself here, but I want to put in something specific here. So this is the default behavior that is inherited from object. If you wanted to, you could override equals in your class and you could provide a value-based comparison. So for example, this circle here and this circle here are two different objects in memory, but they both have a point at x0, y0 and a radius of 1.0. So if I wanted to in circle, I could override equals and I could say two circles are equal if they have the same point, x and y, and they have the same radius, right? That would be more of a value comparison than an object identity comparison. Okay, so I want to emphasize that you could override this behavior if you want to. All right, last one, output number 9. All right, I was comparing strings and it was working just fine. I was comparing strings using equals and it was working just fine. I was comparing circles using equals and it was working just fine. So why can't I compare circles like I do strings with compare to? Okay, this doesn't work. Cannot resolve method compare to. Well, object provides an implementation of an equals method and it doesn't provide an implementation of a compare to method. So string defined its own compare to and it wasn't overridden from object. We can do the same thing for circle. If we want to be able to compare two circles, say we want to find out which one has the bigger radius, for example, we could do that. We would just have to add a compare to our circle class. If we went one step further and we said that circle implements the comparable interface, then we get a lot of really great behavior. Like, for example, we can use out-of-the-box sorting algorithms from Java. Okay, in order to sort, we've got to be able to compare if two objects are in the right order or they should be flipped, right? Which one comes first? All right, so this is a good time now to talk about what is an interface. An interface is a set of methods that a class can promise to implement. One more thing I want to add about interfaces here. So an interface provides a reference type. We're going to see that soon, but kind of a preview. So what I want to do in this video is first talk about the comparable interface, which has one method in it. And that method has the signature int compare to parameterized type t, reference o, which I could even remove here. All right, let me show you where I got this from. I didn't just make it up. All right, so if I go to Google and I type in Java comparable, I'm going to see the documentation for comparable. Okay, so comparable uses a parameterized type. T just represents a type that we're going to specify, and this is nice because it says the type of object that this object may be compared to. For us, this is going to be fairly simple. We're only going to compare circles to circles. So circle will be our parameterized type. Under method summary, you can see that set of methods that any class that wants to implement this interface must provide implementations for. Comparable is really short. It only has one method in it, compare to. Compare to accepts a reference to an object of type t, and it returns an integer, which is the specified object for order, or specified order of the two objects. All right, fantastic. So let's go implement compare to and implement the comparable interface. So I'm in circle, and at the top here, I'm going to put implements comparable, and there's that parameterized type. I want to be able to compare a circle to another circle. Now I want to be really clear here. If we were going to specify a superclass for circle via inheritance, we would do the extends keyword. And since Java only has single inheritance, not multiple inheritance, we always put the inheritance first with the extends keyword, and then we put implements afterwards because you could have a comma separated list of different interfaces that this class implements. Okay, so just to recap, you could only have one superclass, so extends, then one name of a type, but you can implement several interfaces, so implements and then a comma separated list of interfaces. All right, so this broke our code in circle now because it's saying, okay, circle must be declared abstract or implement abstract method compare to. And I'm going to talk about why this says abstract here in a little bit. Okay, so let's provide an implementation for compare to. So I'm going to come down by my toString because I like to put all of my override and implements methods together. It just makes it easier to find them. And I'm going to pull up my override menu with Control O, and I'll scroll down, and here's the comparable interface. It's in the java.lang package. And here's compare to, and that's what I want to provide an implementation for. Notice that just by doing that, our red squigglies went away, and circle.java no longer has a compiler error. All right, so we're going to compare two circles based on their radius. So recall that in order to invoke a non-static method, I have to have an invoking object. So this refers to the invoking object. Okay, that's not something specific to compare to. That's in any non-static method. And O refers to the argument object, which is why we have a parameter here. All right, I'm going to write this in a very lengthy verbose manner to make it very clear. You could write this much shorter than I'm about to write this. All right, so if this dot radius is less than O dot radius, then I'm going to return a negative number. Okay, I'm just going to return -1. If I wanted to, I could return their difference as a negative number to express, the magnitude of the difference, but I don't need that kind of functionality here. I just want to return a negative number to represent that the invoking object should come before the argument object. I'll do the same thing for if this dot radius is greater than O dot radius. Just return a positive number. And if I get here, both of these Boolean conditions were false. So that means that this dot radius is the same as O dot radius, and I want to return 0. I want to say that these are actually the same radius. All right, a very simple working compare to. So now Circle implements the comparable interface. It has a method definition for the one method inside of the comparable interface compare to, and my code is no longer broken. I can run this now. So my circle and my circle refer to the same object, so obviously that object has the same radius, so I get 0 for output number 9. All right. So remember over here when I said an interface provides a reference type? Let me show you an example of what I mean. So comparable is a type. Just like circle's a type, just like object's a type, just like interface tester's a type, etc. Okay, comparable is not a class, it's an interface. So we can't make objects that are of actual type or of actual class comparable, but we can have references that are comparable that refer to actual objects that were created from classes. So I can have a comparable reference type called, say, my comparable, and I can set it to an object made from a class that class implements the comparable interface. Okay, so this is a little preview of polymorphism here. Okay, at runtime, the actual type of my circle will be determined, and that will be dynamically bound to this reference type comparable. I have a large demo of this coming up here shortly, but this is just a little bit of a preview. Okay, now it's time to kind of put this all together, which is we were talking about sorting. If I have an array of circles, I should be able to sort them because they're comparable into, say, smallest to largest order. So let's do that. I'm going to have an array of circles, call it my circles. It's going to be kind of small, let's just say 5. And remember, this is declaring and initializing circle references. It's not actually making any circle objects. So I'm going to come in and I'm going to create some circle objects. All right, for my X and Y, I don't really care. I'll just pass in I and I. But here, I do want to pass in a random value for radius so that these 5 circles are seemingly out of order so that I can sort them. So I'm going to make a random object, and I'm going to call next double to get a random number in the range 0 through 1 for my radius. All right, let's print these out and see what they look like. All right, so 0.66, 0.192, 0.0318. Okay, this is definitely not sorted, right? These are some random doubles in here for my radius, for each one of my circles. All right, so very simply, I'm going to be able to call a utility method in arrays called arrays.sort. And I'm going to pass in my circles. And then I'm going to print out my circles again, and we're going to see that arrays.sort will be able to sort our array of circles because each one of our circles is of type circle, which has implemented the comparable interface. All right, so now in sorted order, I'm just going to check that they keep getting larger, and it looks like they do. Awesome. All right, so that kind of pulls together the first part of the video where we're using an interface from Java called comparable. It has one method in it called compareTo. If we have a class like circle that is going to implement comparable, it has to provide an implementation for compareTo. And we did that, and one of the benefits of doing that is not just that we can call compareTo. We could have done that without defining or implementing the comparable interface, but it's so we can get some behavior like sorting, and sorting only works for objects that have defined a compareTo that are comparable, right? You have to be able to compare two objects in order to determine the order of an array of objects, right? So that was one of the goals. Now for the second part of the video, we're going to start defining our own interfaces. Okay, we don't have to just use the ones from Java. Just like we can define our own classes, or we can use ones that are defined by Java, right? Okay, so the example we're going to do is still in the circle theme. We're going to define an interface called shape. Okay, if something wants to be a shape, it's going to have to implement two methods. And the two shapely methods are compute perimeter and compute area. Like, for example, a circle could also be a shape because it can define implementations for compute perimeter, 2 pi r, or compute area, pi r squared. All right, so I'm going to make a new Java class. You could also just make a plain file. And I'm going to call this shape. And I want to make sure I'm going to change this from class to interface. Okay, shape is an interface. It is not a class. And you can see the green icon with the I in it. Okay, this means interface. All right, so in an interface, you can specify quite a few things. You can specify, for example, static methods, default methods, final variables, final static variables. We're not going to get that crazy or that complicated. We're going to do the most simple, basic form or use case for interfaces, which is providing methods with no bodies, so they're abstract, methods that any class that wants to implement the shape interface has to provide the bodies or the implementations for. So all methods, okay, and this is excluding default and static methods, but all the ones we're going to deal with here, all methods are public and abstract by default. So let's say I do public abstract double compute perimeter. Okay, IntelliJ is going to grade these out and say, hey, public is redundant, abstract is redundant, you don't need these. Okay, we know that now, but we'll just leave them there for now. It's fine. And then for compute area, I'll leave them off just so you can see that you don't need them. But just because I didn't put them there doesn't mean that compute area isn't abstract or isn't public. It is by default. All right, so that's our shape interface. Now let's head over to circle and break some code. So here's my comma separated list of interfaces, comma, shape. So circle is now also a shape. But the compiler is complaining because we haven't provided implementations for compute perimeter or compute area. Now I said a little while ago, I talked a little bit about abstract, right? So we don't have to provide implementations for compute perimeter or compute area if we declare circle to be abstract. But once a class is abstract, you can't create any objects of that type. You would have to subclass it and then create objects of the type of the subclass. And I want to be able to create circle objects, so I'm not going to make circle abstract. Instead, what I want to do is provide implementations for compute area and compute perimeter. So that's what I'm going to do. Control O, really helpful. There's my two methods. There they are. Note the @override annotation. And I'm going to return 2πr. For my perimeter and for area, I'm going to return πr². All right, the red squigglies are gone. We no longer have a compiler error. And now we can head back over to interface tester. And if we wanted to, we could have a shape reference, right? I could say my shape gets, let's do my circle, right? Because my circle is now also a shape. It also has the type shape. All right, so far so good. Now, let's have another class that implements shape so that we can do a nice polymorphism demo. So in addition to circle being a shape, I'm going to have a new class called rectangle, and rectangle is also going to be a shape. So rectangle, instead of having a radius and a center, it's going to have a length and a width. Going to add some basic constructors in here and a basic toString. Okay, this looks good. So we've got an error here because we're not implementing shape, right? We know that we've got to provide methods for those two, or implementations for those two methods in shape, right? Just like we did for circle. So Control O, and there's my two implementations. But for a rectangle, I want to return for its perimeter 2 times length plus 2 times height. Or what did I call it? Width. And then for compute area, I'm simply going to return length times width. All right, this looks good. All right, back in interface tester, I'm going to make a new rectangle. And I'll just test out that everything's working and my toString works. All right, this looks good. All right, so now pulling all of this together and a large polymorphism example. All right, I'm going to have an array of 3 shapes. I've got to stop typing what I'm saying. All right, shape array called my shapes gets new shape 3, pretty small. Okay, remember, shape is not a class. Shape is an interface. I can't make actual shape objects. What I can do is make objects based on some other classes, right, that implement the shape interface, and then that object will have the shape type, but it's not an actual shape object. Okay, it's something else that also has the shape type. All right, so I'm gonna set my shape sub 0 to be my circle. And I'll set my shape sub 1 to be my rectangle. And for now, I'm gonna set my shapes sub 2 to be a new rectangle, but I'm gonna come back and replace this with a nice little example of an anonymous class here shortly. All right, so now I can go through and for each shape in my shapes and print out a few things. I want to print out shape. I want to print out shapes compute perimeter, and I want to print out shapes compute area. And I like to put at the end here just a little divider between iterations. All right, so here's my output from my range-based for loop right here. All right, so my first reference is to a circle, and here I'm getting the toString from circle, right? But I've got the same code no matter what shape actually refers to, right? So when we think about polymorphism, I like to think about same code, different behavior. Okay, so I've got the same code that uses a shape reference. I'm going to print out compute perimeter, print out compute area, because all shape types, okay, have a compute perimeter and a compute area. And all shape types have an object toString, right? Because in order to even make an object reference, I have an object, and that object inherits from object. Okay, so no matter what, we're going to be able to get some output here, even if we didn't override our toString inherited from object in both circle and rectangle. Okay, so I've got the same code here regardless of at runtime what shape actually refers to object-wise. But at runtime, I get different behavior, right? Like this behavior is coming from circle's toString, even though our code doesn't have anything to do with a circle, right? These are all shape references. Here's my results from circle's compute perimeter and circle's compute area. And then my next two references, shape references, are actually two rectangles at runtime. So I'm getting different behavior, right? This is rectangle's toString, and this is results from compute perimeter and compute area from rectangle. All right, another great example of polymorphism right here, right? Same code, different behavior at runtime. All right, so what I want to do now is instead of doing a new rectangle for my shapes of 2, I want to do an example of an anonymous class. This is a great place to do an example of an anonymous class because we have an interface called shape that we want to implement, okay? So I'll leave this here for now, but I'm going to eventually replace this. All right, so this is an anonymous class example. So I'm going to have a reference to a shape called my anonymous shape. Okay, this is the reference. This is not the name of the class. And it's going to look like I'm going to invoke a shape constructor. Okay, there is no shape constructor, right? Shape is an interface. Shape is not a class. If I start to type out new shape, you're going to see that IntelliJ is suggesting curly bracket, dot, 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 curly bracket. Okay, if you press enter here, it's going to provide you the implementation of the anonymous class. Okay, I'm not going to do this right now. I'm going to hand type this all out so I can explain it as I go. All right, so this class is not going to have a name, but it is going to implement the shape interface. Okay, in order to do that, it has to have two methods, right? It has to have a compute perimeter method and it has to have a compute area method. So right after we specify the name of the class we want to subclass or the name of the interface we want to implement, we put our definition in curly brackets for that anonymous class. Okay, this class has no name. Now, it's getting some complaints here because we haven't provided implementations for those two methods, right? So Control O. Okay, and now we have a class definition right here that implements the shape interface but doesn't have a name. That's what makes it anonymous. Okay, this is not the name of the class. This is the name of the reference to an object of type anonymous class. Or I shouldn't even say of type. That is an anonymous class. All right, so just real simply for demonstration purposes, let's say that this anonymous shape represents a 5 by 5 square. Okay, so in compute perimeter, I'm just going to hard code returning 20 And in compute area, I'm going to hard code returning 25. All right, so we have the definition for an anonymous class. We're also creating an object that is of the type anonymous class, okay, but that's not the name of the type. That doesn't have a name because we're invoking the new keyword here. And now I'm going to replace my shape sub2 with my anonymous shape. And I'm going to run this and everything's going to work just fine because my anonymous shape is of type shape. Okay, it's also a plain old generic object, right? But I'm making an array here of shapes. All right, so nothing changes up here for our first two shape references, but down here you can see that I'm getting some strange output when I'm trying to print out the object that shape in this for each loop refers to. And if you look at this, you might be able to guess where this is coming from. So this is the output from objects toString because we never overrode objects toString in this class definition like say we did in circle or in rectangle. So this is just inherited behavior from object, okay? All right, and then there's 20 and there's 25 coming from my compute perimeter and compute area methods. Not to get too crazy on you, but I don't even need a name for a reference to this object that was created using this anonymous class. I could do this. Cut, goodbye anonymous shape, and assign directly my shape sub2 to refer to an object created using this anonymous class. That's no problem, I can do that. So it might seem kind of crazy, like why would you do this? Why would you do an anonymous class? Why would you even want to implement an interface without giving a name to the class that's doing the implementation? Well, one example is event-driven programming. So in event-driven programming, you're implementing something called a callback. And a callback essentially registers itself with a graphical user interface component, like say a button, and says, hey, whenever you're pressed or tapped or whatever, go ahead and execute this method in this class, okay? You could go ahead and define a class that implements that interface that provides that method, in its own file or elsewhere. But your code is going to get unnecessarily long, and it can be a best practice to declare that class when you're using it, meaning when you're registering that class as a callback or a listener of a GUI component, graphical user interface component. So in that case, you're only going to use it once in the code, okay? I'm not saying it's only going to be executed once, but it's only going to exist in the source code in one spot. So why not couple it tightly with where it's being used, declare the listener at the same time in the same place that you are registering the listener, okay? If you work with, say, Android, or you work with Java Swing or a Java graphics framework, you'll see this used quite extensively, okay? It makes your code shorter and it makes your code easier to read and maintain because you're defining the class at the same spot. You're creating an object of that type to register it or to use it in that one spot in the code. Okay, so that's it for interfaces. Just to recap, we saw an example of an interface that is provided to us by Java called comparable, which allows us to sort objects of type classes that we define ourselves as programmers. And we also saw how we can define our own interfaces with shape, and how interfaces, very similarly to inheritance, allow us to exercise polymorphism in our code, where we can treat different types similarly based on an interface type or a superclass type. And that's really nice. So we can write shorter code without having to test types at compile time. And then at runtime, those references will be dynamically bound to objects of, say, a different type, like a subtype or a subclass. All right. Thanks. Thanks for watching, and hopefully everything is clear about interfaces.